Right, so when I left you all last week, I showed you all this. Right, last week I showed you how to find the root mean square current. And I showed it for two specific cases, one of a square wave and one of a sinusoidal wave. And I showed after that the power. The mean power is root mean square current squared times the resistance. Right, and for sinusoidal, very interestingly, the mean power is half of the maximum value. Right, this is where we left you at last lesson. Demonstration of gravity. And this is being recorded, so this is going into eternity. You will hear laughter in the middle of if you are at home right now and you hear a sound of laughter, this is your friend demonstrating to you gravity. Right, so part E and part F is what we declare to cover today. Alright, so let's not wait. Transformers. There's this scary looking picture. Right, so I assure you I'm going to cover this in detail so that you actually know what's going on. So don't be scared by this. Right? Next I show you the picture of what it looks like. It looks just like a dustbin, right? Shape of a dustbin, but what is important is what's on the inside. Okay? First thing, what is the use of a transformer? Right, is to ensure that the voltages can be stepped up or down easily. Let me just check that my recording is going on. Yes, it is very good, because if not, I got to spend 1 hour to restart and I'm losing my voice. So the usefulness of the AC is that it can be stepped up or down. Why is that important? Because if you can step up the voltage using V equals to IR, you know that you will reduce the current. And once the current is reduced using P equals I squared R, where I is the current through the cables and R is the resistance of the cable, the power will be reduced. This is a very important concept, and we will see that later on in one of the examples, how much money we can save. Okay? So this is the usual circuit diagram. Right, on the left-hand side, you have the AC generator, the power station. The pink color wires are the long-distance transmission cables. And this end would be your step-down, your substation before your home. So if you translate this to a real picture, your power station is this, right? You have a power plant, which is here. Then this, which is the circuit diagram for a transformer, is the transmission substation right here. The pink color one is the high voltage transmission wires. In Singapore, you don't see this. Do you know where they are? It's underground, right? If you actually travel to Malaysia, or you look at some of the shows in the US, you see these huge things called the pylons where the wires are transported. Okay. Next, you have a transformer drum, which is to step down the power. So actually, there's two. There's one power substation already to step it down from a very high voltage, and then there's a transformer to step it down even further. And then there's in your laptop, right, like this, another transformer to step it down to the necessary voltage inside your laptop. Okay. Right. So last week I introduced to you this mustache handsome man, right, Nikola Tesla, and I told you that he's a genius. Unfortunately, in the current day and age, you think like a genius will have a good life, but actually not true. For him, I think he had a very, very bad life. I think he died a pauper, right? Being very poor. Why? Why? Huh? One of the problems was actually Edison. Edison, a great man. Right? Remember when we are younger? I remember when I was a child. Edison invented the light bulb, and my mom always used that story to encourage me about the virtue and value of perseverance, right? Have you heard of the story? Edison tried many materials to make his light bulb. And every one material that failed, he said, it is not one more way, it's not because I failed one more time, it's because I found one more way to not do it. So after 1,000 tries, he finally found and built the light bulb. That was the story, right? But when I then grew up, these are all fairy tales. In reality, right, when I saw the story of him versus Nikola Tesla, in this situation, he wasn't a very, very nice man, right? So what happened? Thomas Edison came first. He was the more prominent scientist. He came first. He's more older. He proposed powering everything by DC. There's a certain reason why. If you are looking at your laptop, if you're looking at your handphone, it needs to be charged by a DC. It cannot be charged by an AC, because if it's charged by AC, it will power up half the time, and you will depower, you will unpower it, you decharge it the other half of the time. So it wouldn't really work. If you're looking at your fan motor, right, it must turn in a certain way. You cannot have your fan turning halfway and then turn back, halfway and turn back. That's not going to be a very powerful fan, right? So there are some ideas there by Edison. However, there are crippling weaknesses in this idea. Why? Because to send DC at that kind of value, you are sending current through your wire. You need your wires to be really, really, really thick, right? So your current value can be as low as possible. Right? So imagine if I have a 2-kilometer line of copper wire, I need the copper wire to be about this size. How much copper is that? How much will it cost? It's a huge, crazy amount of money, right? Also, next, the voltage cannot be easily changed. Although with modern electronics, this has been solved, right? I remember I stepped out of the lecture and somebody said, one of the students said, no, Mr. Oh, look, it's been solved. I'm like, yes, okay. But that was then, right? Thank you. Right? History. But back in time, no. So why is Nikola's system better? One, because you can step up the voltage, the current can be reduced. The current can be reduced regardless of the resistance of the cables. You can reduce the power losses. Okay. The second thing is that because your wires can be very, very long, your plants can be very, very far away. Can you imagine you are in VJC and next to you is a power plant burning diesel or coal or nuclear power plant? Right, we'll be glowing green by the end of the lesson, or be choking from the smoke, right? So those are all the bad things, right? Well, obviously Thomas Edison didn't care. Right, so he died a poor man, sad. Right, so today we're going to see why it works. Okay, do you own a transformer? The electrical one, not the toy one. So this is a transformer inside. There's a transformer in your book. Okay, your handphone charges, all these are transformers. There are a few ways to represent it. This is the picture. This is the circuit diagram. Sorry, this is a circuit diagram, circuit symbol. And this is the one that we use to teach you in the lesson. However, please do not go away thinking that we will always have a donut shape. There's a square shape and have the two wires side by side. In reality, the wires are caught one over the other. Why is this so? Later on in this lecture, I'll talk about the losses in the transformer. Right? This is actually to prevent the loss of magnetic flux. Right? If you put it one over the other, the magnetism, transfer of magnetism is actually better. Okay? Right, moving on. So example number 7, right? So let's look at number 7. A nuclear power plant is generating power of 2.0 megawatts. Mega means million. Electrical power, transmitting this through cables with a resistance of 5 ohms. Find, part A, the power loss in the transmission cable if the input voltage is stepped up to 500 kilovolts before transmission. B, the loss in voltage in the cable. C, the output voltage at the destination load. And D, recalculate the power loss if the input voltage has only been 5 kilovolts instead. Let's do it step by step. Right, so with this diagram, Right? Sometimes you have to draw this diagram on your own. Do note that you sometimes have to draw this diagram on your own to help yourself visualize it. So first, if your power is 2.0 megawatts and your voltage is 500 kilovolts, which is pretty high, right? The current will be 4 amperes, right? Using P equals to VI. Then the power loss using P equals I square R will be 4 squared times 5 equals to 8 watts. Okay. Next, there's a voltage drop across the cable. Do note this voltage is not a voltage across the power station. It's a noisy, the voltage across end user is a voltage drop across the wires. So there's a voltage drop of 20 across both wires, which means there's a drop of voltage of 10 across the top wire and 10 across the bottom wire. Which means that if this point, if you look at the screen, right, look at the screen, this point is 500 kilovolts positive potential. This point at the home must be 500 kilovolts positive minus 10. If this is 0, this must be plus 10, right? Because it's 20 volts across both wires. Across each wire is actually 10 voltage drop. Okay. Next part C. What is the output voltage at the load? Essentially, it's just 500 kilo, 100,000 minus 20. So you get this value. Okay. So notice here there are a few things. There's number 1, the delta V across the power station. Number 2, there's the delta V across the load. And number 3, there's a delta V across the wire. Right? Okay, there's these 3. Why is this important? Why am I highlighting this to you? Because when we calculate the power, I suggest to you to use I square R. But can you use the equation V squared over R? The answer is yes, you can. However, there are 3 V's here. 500K, 20, and 499.98K volts. Which one do you use? The answer is you should use the 20. If you're going to use V squared over R, you must use the V across the cables. But because there are 3 different V's, to help you think through this concept, I just say use I square R. It's so much faster. Okay? Can you make a note now on your paper? Okay? Next, part D. Part D is a question that I add in to help you get a sensing of how much money you are wasting. Okay? If the input voltage was actually 5 kilovolts, 5 kilovolts is not lower by any chance because our mains are 240. Right? So using the same method, the power is 2.0 megawatts, the voltage is 5,000. I find a current of 400 amperes. Finding the power loss in the cable, I use I square R, I get 800,000 watts. Now think about this. How much power are you producing? In the power station, it's 2.0 mega. This is 0.8 of a mega. Do you agree? This value here. Which means if you believe in Edison, for every $2,000 of oil you buy and convert to energy, let's say you convert that completely efficiently, how much oil, or how much money are you losing when you transmit through a low voltage system? Every $2,000 you're wasting 800 leh. Does it make sense to you? Right? It does not make sense, right? Does not. And let's compare Tesla's method. If I give you $2,000, which is equivalent to 2 megawatts, how much money are you losing? You're losing a fraction of a cent. That's just how much better Tesla's method is. Right? Tesla is awesome. But the world doesn't understand greatness. Saying it as if I felt it. Right, moving on. Example 8. Now, be very careful. Just now I told you how many V's are there. There's a V across the generator, there's a V across the wire, and there's a V across the load. This V is which V? This V is which V? Is the V across the generator. Okay, be very careful. So how do we solve this? So any instance, power is the V across the generator times the current through the system. We can rearrange to get this value. Next, power loss, we have P equals to I squared R. We sub in I equals to P over V. We can see that power loss is proportional to 1 over V squared, where this V is the V across the generator. So the higher you pump your voltage or potential difference across your wires, the smaller the current, the less the loss. Okay, notice very clearly what this P is. Okay, I'll give you some time to copy down and make that note. Very important. Right. We have until 2 p.m. Right? Okay, good. We are on good time, making good time. So I have a question here. Why don't we keep increasing the V? Why don't we just make the V 100 gazillion volts so the current is 0? Why do we do that? Would that work? Theoretically, it will work. Right? On piece of paper, it will work. But why does it not work realistically? And the answer comes in the form of lightning. How does lightning form? Lightning forms when the cloud and the earth is of a different potential difference. When the potential difference is so much that you can ionize the air between it, you will ionize the air between it and the electricity will go through, and that is actually your lightning. So if your power station, if you keep upping the voltage, right, you'll reach a certain stage where you are essentially breaking down the air. Your power station, you'll see how electricity is like that. And you are just heating up the air, which you are wasting energy. So there is an upper limit. There is an upper limit. As far as I know, I think it's around the region of 240 kilovolts. I think that's the rough amount that I read, right? That they convert it up to. Right. Next, I need to tell you how does a transformer work. There are two ways of describing it. I'm going to do the simple way with no equation, which is important because it helps you answer many of the qualitative questions. But there are some there's another way which is more intense, is in your Annex A. I will go through once in this lecture. Okay, first, what is happening? If you apply an alternating voltage here, there will be an alternating current flow in this coil. You see where my mouse pointer is? Okay, I am not standing to the screen. I'm seated down because I need to show the viewers at home. Right? So there will be alternating current here. If you have alternating current here, using your right hand grip rule, what will happen? You'll have an alternating magnetic flux, right? Right, the viewers at home can try quickly. The coil, you see a BQ point up and down. So what happens? In this coil, you see these blue lines. What are these blue lines? These blue lines are the magnetic flux. If you have an iron, a soft iron, this flux generally gets channeled very well within the donut. Which means if you have a magnetic flux that goes up and down on the primary side, you will have a magnetic field that goes down and up on the other side. Right? If this turns clockwise, this is clockwise, this is up here, this is down. When it turns anti-clockwise, this is up here, this is down. Right? So there will be alternating magnetic flux on the secondary side. So until now, we are using what you have learned in electromagnetism. Right? Electromagnetism. Now, next concept. So transformers is the application of actually both topics. Using concepts in electromagnetic induction, by Faraday's law, a changing magnetic flux. And you put coils here. So the coils will detect a changing magnetic flux linkage. By Faraday's law, alternating EMF will be produced. Right? Faraday's law states that, okay. So until here is actually 90% of the picture. Okay. Most standard qualitative questions requires you to explain step 1 to 4. Done. 4 points. There are 3 more points that I want to mention. 1, if this circuit is complete. So until here, if the circuit is not complete, it will still happen. But if the circuit is complete, what will happen? When the circuit is complete, this potential here will cause a current flow in this circuit, either clockwise or anti-clockwise. If there's a current flow through a resistor, there will be a power consumed on the secondary side. Which means, by conservation of energy and hence power, right, there must be power produced here. Then step 7 is where the magic happens, or rather the hand waving is. Here, I just say that, oh, the potentials are stepped down, the voltage here in the primary side is stepped down to the secondary side, or stepped up. But this side is a little bit more hand wavy, because you will notice that step 1 to 7 does not help you get step 7 logically. Right? So to explain step 7, you must listen to me and listen and read the annex. Okay? So step 1 to 6, I applied concepts from EMAG and EMI to explain how the functioning of transformer works. To explain how it works qualitatively, I have to explain to you the annex. Right? And I'm going to just do one small part of it. The key idea is this. If your donut is well designed, if you have caught the wires one over the other, the number of flux in the primary side is equal to the flux on the secondary side. Then, which is also essential, which is also equal to saying that there's no blue lines escaping the square. Okay? So if the flux is the same, this looks like a satay stick, right, with a fishball. So if you have 3 satay sticks on this side, you will have 3 satay sticks on the right hand side. the rate of change of statistics on both sides must be the same. Right, so the rate of change of flux on the primary side must be equal to the rate of change of flux in the secondary side. Do you agree? So from this top square that I've highlighted here, I can get this equation. Next, if my wires have no resistance, how much potential difference I put in the source is how much potential difference I have across the coil, and how much EMF I produce in this coil from Faraday's law is how much PD I have across the DS. So this equation then becomes like that. And if you then look at this equation, I can bring NP down. I get VP over NP equals to d phi dt. And on the other side, I get Vs over Vns equals to d phi dt. Which is to say, Vp over Np must be equals to Vs over Ns. The in-between of d phi dt is taken away. And this is how you got your transformer equation in your secondary school. Okay, this is A levels, right? We cannot ask you to do the same thing as your O levels. So this is actually important. Although I have not yet seen an A level question that tests this, from what they put in the learning outcomes, by right, this is inside. But by left, I know it's difficult, so I put it in the annex. So you read it once, you get a rough idea, and you are done. Okay? And if you're the ones that are going for the full credit of A, you might want to revisit this slide again in the video. You just want to note down, revisit this video. Okay? At this time. Right. Done. Right, so I've proven to you why Vs over Vp is Ns over Np. Right, and this part is a secondary school you all should have learned. If it goes up, if a Vs is higher, it's a step up. If Vs is lower, it's a step down. Okay? And the more important thing is, we assume that the power, the transformer is ideal. That means the power conversion is 100%, which means the power in the primary circuit is equal to the primary power in the secondary circuit. Rearranging, we get this. And then we realize that if we combine all equations, we get this. So this is the box at the bottom is the one equation to solve them all. Right? The one equation to solve them all. But you notice how I get each part of the equation uses different concepts. Right? To get Vs over Vp equals Ns over Np, you need to use many concepts. Whereas to get Vs over Vp equals Ip over Is, you need to use ideal transformer. Okay? So the concept behind is important. I better move on. Right, so let's use one example. You have 10 lamps rated 24 watts and 12 volts. So again, 24 watts, this 24 is the average power. 12 volts, remember last lesson we said rating, 12 volts means what? The 12 volts is the 12 volts VRMS. The mains is 240 volts. This volts, is it also VRMS? Yes. So these are all VRMS. Okay? So you use all VRMS. In your turns ratio, notice you have Vs over Vp. We are comparing Vs, secondary side RMS, versus Vp RMS. Okay, I never put that in because if not, it will be such a long and chunky subscript. But I'm comparing RMS to RMS. I can do this. So once I put that in, I get 1, 2, 12 over 240. Here, I also want to point out something. Turns ratio. Turns ratio, by definition, in most textbooks, or the textbooks that actually define them, is secondary over primary. Okay, I will hate for you to solve everything perfectly, and then the question is, what's the turns ratio? Then you don't know whether to put NP over NS or NS over NP. Is it S over P or P over S? They are like, oh shit, it's a 50-50, right? So this information I need to tell you is secondary over primary. That's how most textbooks label it. Of course, there are some questions that go against the norm. They say there is a turns ratio of primary to secondary of 1 to 20. There are some books that do that also. So you have to open up your eyes and check. Okay? Right. So to complete, the turns ratio is 1 to 20 or 0.050. Okay. B. What is the current drawn from the mains if the transformer is 100% efficient? That's something to do. So each lamp will draw a certain current. So this current is P equals IV, IRMS equals to power over PRMS. So you get 2.0 IRMS. You have 10 lamps, so the total current being drawn from this part of the wire, this part, would be 20 current, 20 amperes. So the total power using P equals to IP. So secondary side will be 12. The VRMS is 12 VRMS. I is 20 VRMS. IRMS. Multiply together, you get 240. So you get the primary current, root mean square current, at 1.0 root mean square current amperes. Okay? This is how you do it. So we use power to solve. Here is example 10 that you don't have in your notes. Can you take 5? Actually, it's an MCQ question, but I give you 3 minutes instead of 2. 3 minutes to try to solve for this value. This is also in your supplementary tutorial question, so solving it here, you will solve your supplementary. Try. Take a picture or whatsoever, then try. 3 minutes starting from now. Okay, so how do you solve it? Let's see. There are many ways to do this, right? They say the peak voltage is 180. So you can actually down convert it to find that there's 90 on the secondary side. You can do that. But if you are like me, I like to work with RMS, so I will take 180 on the primary side. I'll divide by square root 2. I'll find that the root mean square voltage on the primary side to be 127.3. Then I will step it down. I'll divide by 2 to find it 63.7. That means at the secondary side, the root mean square voltage is 63.7. Then using V equals IR, I know V is 63.7. The resistance is 120. The total current is 0.531. Then using P equals I square R, oh my god, right? It's a 0.531 square times 80, 23 watts. Answer is B. How many of you got this? Okay, how many of you didn't? Okay. Right. Yeah, and this is an A-level question. It's an A-level question. A bit more on the slightly challenging side because you have 4 equations to work through. Slightly challenging, but still A-level. Okay. Right, moving on. We talk about power losses. Right, remember we said that in the equations that we have, the transformer is always ideal. But it's not always true. There are actually 4 main reasons. This efficiency, yeah, we always take it to 100%. Actually 4 main reasons, and it's this form. Eddy currents, resistive heating, hysteresis, and leakage of magnetic flux. I'll explain each of them carefully. First, eddy currents. You have a current that's going into the coil like this. If you use your right hand grip rule, you will see that you'll generate a B field upwards. Right, so first is the current. Look at the current. You go in. If the current is increasing, the amount of B field here will be increasing. Agree? So the current is this way. If the current is increasing, the amount of B field is generated is increasing. So it gets stronger and stronger, pointing upwards. So that is your Emax side. Now let's use electromagnetic induction. If you have an increasing B field pointing up by Lenz's law and Faraday's law, by Faraday's law there will be EMF induced, and if the complete circuit there will be a current. By Lenz's law, how we do like you will counter this B field, right? You use a right hand grip rule, but now you try to point downwards. You try to generate a B field that points downwards that counters this increase in B field. And you'll see that it creates a current that turns clockwise like this. Okay, and this current, we call it the eddy current. Special name, we just don't call it any current, we call it the eddy current. I think it might be invented by a person called Eddy, or might be invented by a person that don't like eddy. Because eddy current generally means the current that you don't want. Okay? So I presume it's the first one. The scientist called Eddy named this. So this current will create I square R will create power losses. So how do you then limit these losses? Well, you make the resistance higher. How do you make the resistance higher just for the eddy current? You laminate it. Previously, your cross-section of the core looks like this, right? So the current can flow very freely and happily. If I look from the top, right, this is my eye, and I laminate it, then I look from here, what do I see? I will see metal, a laminate which doesn't conduct electricity, metal, another laminate that doesn't conduct electricity, metal, so on and so forth. And how would my current flow? My current will still flow clockwise, but the resistance is so much higher now because it's so hard to flow. There'll be many tiny currents created. Right, so by laminating it, it actually reduces heat loss. Okay. So eddy currents we can prevent. Next, power loss is in the resistive heating in the coils. So P equals I squared R. The coil itself has a resistance, so P equals I squared R. That one is quite direct. Okay, resistive heating in the coils. The third way of losing energy is hysteresis. And at this point, I will lose a few of you that say, wow, hysteresis is so hard. What a difficult word. It's not, right? The idea is this. The iron core will have a way of magnetization. It's made out of many small domains that points up or down, right? Like this. So iron, if I look into it, there's many small cores that points in random direction. If I place a certain B field, it will align to it. Right? So if I point this way, and later I point the other way, it will align back the other way. So the B field will keep rotating. Right? See? It will keep rotating. And the analogy is this: if you stand in a very compact MRT and you try to rotate yourself every other time, I think your passengers, your co-passengers will hit you, right? Because you are doing a lot of friction. And you're hitting them up. Then they'll hit you. Right? So the same thing is this: when you're rotating your magnetic domain, there is some heating up of the metal, which causes heat loss. Okay? So some work needs to be done to rotate the magnetism direction. Right, moving on. 4, flux leakage. Right, remember just like I said, there's a blue square dotted line. There's a flux, but flux can leak. If I point a magnet like this in a certain direction, it doesn't go all the way. I mean, it gets lost. Right, if I point it and I'm at the wall, I cannot detect the B field. Same thing here. The magnetic flux can be leaked. Right, so these are the losses. So you need to know all these 4 losses. It could be the question could be state 3 ways in which energy is lost in the transformer, or it could be state how eddy currents causes losses in a transformer. So you could need to go into more detail depending on the question. Right. Last one, we are now going to talk about part F, about using a half wave diode to rectify it. Oh, I'm going too slow. So this is a diode, right? And the diagram, it points to the right. The play sign indicates the direction of flow of the current. Okay? So when the current is in the direction of the diode, it will allow current to flow. We call it the forward bias. When the battery is in the opposite direction, the current cannot flow. This is called the reverse bias. Okay, so what would happen if you connect a diode into an AC or alternating voltage? This is your applied voltage. It goes up and down. It's an AC. You put a diode there. Half the time the voltage will disappear because no current will flow. You will find nothing there. So half the cycle disappears. Okay, so you get this, AC becomes a DC. Remember I said if it's constantly pointing the same direction, it's called a DC, even if it varies. So you get AC to DC, and this is what Tesla was proposing, right? You have, using diodes, you can simply rectify the circuit. Okay, we'll skip that. That's just a recap of the PN junction in your COE notes. Okay? So what example? What is the root mean square current of this rectified circuit? So in an exam, the graph may not be given. They may just give you the word text. Okay. So first, root mean square current. We learned last lesson. How do you do it? You must first square it then you must do the mean. How do you mean it? Well, you notice that for the first half of the period, the mean is 40.5, right? That's what we learned. Next half of the time is 0. So if I give you $40, then 0, then 40, then 0, then 40, what's the average? Average will be 20. So same idea here, the mean value here will be 20.3. So you have squared it, you have mean it, now you must root it, right? So root it back. So square it, take the mean, find it to be 20.3. You root it, you find that it's 4.5. And the amazing thing happens. The maximum value is 9.0. You realize that the root mean square current is actually just half of the maximum value. Interesting? Interesting, huh? Because if you take the mean value, it's going to be a lot lower. Not a lot, I mean it will be definitely lower than 4.5. The mean value of a rectified circuit will be lower than the root mean square value. Okay? Calculate the power. Power is just I squared R, put it in, you're done. And you notice something else. In the non-rectified sinusoidal wave, the average power is half of the maximum value. We learned that last week. Here, we realize that because you remove the power half the time, the power that you must give must be half of what you have previously. So P0 over 2 becomes P0 over 4. Right? It's a very logical deduction. Right? So I also gave you a summary. These definitions are important, especially the first one. I also gave you a summary of the equations. Wait, don't go. I gave you a summary of equations to use. I also gave you the equations for the ideal transformers. Number 6, please refer back to the page where I have all the words about how it's lost. Wait. So now, if you only have a one diode rectification, how will your radio sound? It was like this. There will sound the time. Half the time there will be no sound, right? You agree? Because you have no current, right? So what can you do? You can actually do something called the full wave rectification using 4 diodes. I'm going to show it to you. When I was a student your age, I gained so much pleasure understanding this. So I'm going to share my pleasure. So when the voltage is positive here, it goes up, comes to the right. It cannot go through this, so it must come down, go to the right. Look, the current in the resistor is downwards. It will come back, go up. At this point, it cannot go back up because the top point has a higher potential, so it must go towards the lower potential, so it goes this way. When the voltage flips around, it will come to the bottom point here. You cannot go through this because it's the wrong direction, you must go up, come down. Notice in the resistor, it continues to point in the same direction, downwards, to come back. Once it comes back to this junction, it can flow either up or down, but it cannot flow down because if it flows down, it's going to a higher potential. So it has flow up to the lower potential, come back down. So you notice, regardless of how the AC flips, your current points down. You have fully rectified the circuit and you don't have spaces between. You have saved energy. But this is still a problem because if this was true, your radio will sound like this. Correct or not? Because the voltage it's not constant. Right? Your radio, your speaker will sometimes be loud, sometimes be soft. So there must be one more thing, and this is purely of your syllabus, right? Purely of your syllabus. we must put something called a capacitor to smooth out the voltage. Okay, and this is how you change from AC to DC, and this is what Tesla has thought of, and this is what we are using now. Thank you very much. Have a good day. Bye bye.